Hello everybody, my name is Kai Cui and I'm from Technical University of Munich. In this video, I'm going to present our work Convolutional Neural Network Based Post-Filtering for Compressed YUV Photoresist Images and Video. This work is collaborated with Huawei Technology in Munich, Germany. Image and video compression are very important for image-video transmission and storage. The raw data size is too large to store or transmit. For example, for a raw 20 megapixel photo, it's about 57 megabytes, and for a 1 minute 1080p video, it's about 10 gigabytes. That's why many lossy compression algorithms are proposed for image and video compression. However, lossy compression brings compression artifacts, like blocking artifacts, raining artifacts, and color leaking artifacts. Left-hand side figure shows the images compressed with JPEG compression of quality factor of 10. From the zoomed-in patches here, we can see that after compression, there are a lot of visible blocking artifacts, raining artifacts. Right-hand side figure shows a video sequence compressed by the latest video coding standard VVC. From the zoomed-in patches here, we can observe some color leaking artifacts and also raining artifacts. These artifacts will downgrade the visual quality of the image and also downgrade the performance of computer vision tasks. That's why many post-filtering algorithms are proposed for compression artifacts removal. However, most of the existing CNN-based post-filtering approaches are designed for grayscale image or for RGB images. For example, the ARCN, DNCN, and three-stage neural network. The YUV photoresist format is the most often adopted format in image and video coding, and it has some special characteristics. First, the Y channel and UV channel have different spatial resolutions. And then the Y channel contains more high-frequency details, and the UV channels are more smoother. Third, the U and V channels, they are compressed more aggressively in the codec. And for Y, U, and V3 channels, they have very large dynamic range differences. The figure right-hand side shows the normalized dynamic range of the Y channel, U channel, and V channel. The box plot shows that the Y channel covers a very wide dynamic range, and for U and V channels, they cover a very limited dynamic range. Inspired by these characteristics and our previous work, we propose a three-stage convolutional neural network-based post-filtering network for YUV photoresist format. The network structure is shown in the figure. There are three stages in the proposed network. The first stage is used to enhance the Y channel, and the second stage is using the enhanced Y channel to guide the reconstruction of U channel and V channel. In the third stage, the three channels are refined jointly. For each subnetwork, a network structure shown in the bottom left is adopted. The network structure is designed based on the YUV photoresist characteristics. Since Y and UV channel have different resolutions, we introduce the pixel shift and pixel unshift modules to make the concatenation possible. Since Y channel has high quality details and UV channel are aggressively compressed, we use the Y channel to guide the reconstruction of UV channel in the second stage. And due to the Y, U, and V channel, they have large dynamic range differences. The reconstruction of Y and UV channel are firstly performed in the first and second stage, and then jointly refined in the third stage. Here are some experimental details adopted in our experiment. For training dataset, we are using the DIV2K dataset, which has 900 images of 2K resolution. We convert them to YUV color space with BT709 standard, and then downsample them to YUV 420 format with bilinear downsampling. For testing, we are using the JVAT standard testing sequences. There are 26 of them, and the resolution is from 240p to 4K. For compression algorithm, we are using the VVC 10.0, and we apply the all-intra configuration, and the quantization parameter is set to 2227, 3237, 4247. For each subnetwork, we are using 10 convolutional layers, and the loss function here is a weighted MSE loss. The batch size is set to 64, and the patch size is set to 160 by 160, and there are 45 epochs in total. Adam Optimizer is adopted to optimize the parameters, and the initial learning rate is set to 1 to the power of -3. First, let's look at some visual quality comparison. We take some image patches from 3 example sequences and zoom them in. From the zoomed in patches here, we can see that after VVC compression, there are some visible color leaking artifacts, raining artifacts, and color stripes. With the proposed post-filtering, these artifacts can be well removed and the visual quality is improved. Next, let's look at some objective evaluation results. Here we take the average PSNR as the metric, and the table shows the PSNR of the compressed sequences, of the sequences with post-filtering, and the PSNR gain between them. From the table, the first observation is that the PSNR gain is target quality or quality parameter dependent. For lower target quality, for example like QP47, the gain is about 0.25 dB for Y channel and 0.6 dB for U and V channel respectively. However, for higher target quality, for example for QP22, the PSNR gain is quite small for Y channel and 0.3 dB for U and V channel. This is because for high target quality like QP22, after compression, the PSNR is already larger than 43 dB. It's very difficult to improve them further. Another observation is that the PSNR gain is channel dependent. They are more efficient for chrominance channels. Even when QP equals to 22, we can see 0.3 dB for U and V channels. We also calculate the beyond-gut data bitrate improvement to evaluate the performance of the proposed approach. First, we use QP32, 37, 42, 47 to do the testing. The testing sequences are the JVAT sequences, and they are classified to A to F based on the resolutions and content. From the table here, we can see that the proposed post-filtering achieves about 59% for Y channel and 17.6% bitrate saving for U channel and 19.1% for V channel. Next, we also test another 5 QPs, 22, 27, 32, 37, and 42, which are mentioned in the JVAT common test condition. For these 5 QPs, we can achieve 3.6% for Y channel, 12.75% for U channel, and 14.93% for V channel. For VVC post-filtering, Many approaches are designed to be able to turn on and off and can select different models. We also simulate this frame-wise turning on-off and model selection. As shown in the table, for most of the classes, turning on and off brings very minor improvements. This means under most cases, the CNN-based post-filtering is enabled. And similar happens for the model selection. The model selection also brings very minor performance improvements. However, if we would like to enable on-off and model selection, we need to modify the encoder and encode the flags into the bitstream, which will make the codec not compatible with the standard encoder and decoder. Next, let's look at some ablation studies. A very straightforward way to deal with the YUV420 format is to train 3 separate models for Y channel, U channel, and V channel respectively. Another solution is to train a single stage network jointly for Y channel, U channel, and V channel. We also trained these 2 types of networks, and the results are shown in the table. To make it a relatively fair comparison, we tune the number of layers to make sure these 3 networks have relatively comparable number of parameters and complexity. From the average PSNR numbers in the table, we can see that for the 3 separate approach, for Y channel, the performance is comparable. However, for U and V channel, we suffer from a large loss. This means the guidance of Y channel is crucial for U and V reconstruction, and it also means the Y reconstruction mainly relies on the Y channel itself. When we look at the single-stage model jointly trained for Y, U, and V, we can see that for Y channel, it performs comparably to the other 2 models. However, for U and V channel, it performs worse than the 3-stage model, but better than the 3 separate model. This means that interchannel correlation between Y and UV are partially exploited in the joint single-stage model. However, reconstructing 3 channels simultaneously of such a large dynamic range differences jointly with a single-stage network is not optimal. These ablation study results further prove that the rationality and effectiveness of our proposed network design. Finally, in conclusion, YUV420 format is the most adopted format in image and video compression. It has some special characteristics compared to images in RGB format. The proposed 3-stage convolutional neural network-based post-filtering approach is specially designed for YUV420 format. Due to the resolution differences between Y and UV channel, we introduced the pixel shift operations. Due to the high-quality details is in Y channel and UV channels are more aggressively compressed, we use the Y channel to guide the reconstruction of U and V channels. Due to the large dynamic range differences between Y channel and UV channel, we reconstruct Y, U, and V channel in different stages. The proposed post-filtering method achieves 3.6%, 12.75%, 14.93% BD rate improvement over the VVC 10.0 codec for all intra-configuration for the JVAT testing sequences. The ablation study shows the effectiveness of the proposed approach compared to training 3 separate models for each channel, or training a single-stage model for all 3 channels jointly. I would like to thank you for your attention, and I'm looking forward to discussing with you in the live Q&A session.